Okay, kids. Now that we know Kirchhoff's laws, we can solve basically any circuit. That's pretty great. Oh, but Mr. Lamb, Kirchhoff's laws was so hard. I watched the video like 5 times. I didn't understand it. Yeah, and I didn't watch it. I also didn't understand it. Well, if you guys really want, I can teach you guys a shortcut that'll help make Kirchhoff's laws a lot easier and complicated circuits much easier. But it might take a while. It might be a double lesson. Is that okay? Yeah, that's fine, because I love physics so much. Okay, let's talk about a very nice shortcut called REQ, equivalent resistance. Um, do this. Easy question. Since V equals IR, 12 volts over 6 ohms is 2 amps. That's correct, but really, in your mind, you're actually drawing a loop. A loop will go through the battery. If it's hypothetically a loop that's clockwise from the left side, you'll go through the battery, gain 12 volts, then you'll lose voltage I times R, which would be I times 6, so then I must be 2 amps. So yeah, it is just V equals IR, but really you're using Kirchhoff's laws. You're drawing a loop, and then for the loop, you say the total voltage gained and lost must be 0. Okay, so that's fine, but that's not fine for other kinds of circuits. And to illustrate those kinds of circuits, let's imagine not circuits. Let's say I have a giant tank of water and another tank of water and just one little pipe. Let's say this tank's full of water, this tank's empty. I stick this one pipe in and I start draining the top, but it's taking too long. I want the pipe to drain 3 times as fast. So my boss gives me 3 pipes. I'm going to replace the one pipe with 3 pipes, and hopefully that'll make the water drain 3 times as fast. So instead of one pipe, I'll have 3 pipes. 1, 2, 3. Will this allow my water to drain 3 times as fast? Why not? This is no good. A bendy pipe, 3 times as long, but it's still very small and narrow. This is not going to be 3 times as fast. This might actually be 3 times as slow. This is no good. If I want faster drainage, I should put it like this. 1, 2, 3. These 3 pipes will drain the water 3 times faster, approximately, in theory. This setup is known as the pipes are in parallel, and this setup is known as series. But it doesn't actually matter what the pipes look like. It matters whether the water or the flow goes through one, then the other, then the other, a series, or one or the other, or the other. That's parallel. So let me draw 2 basic circuits. Here's the battery. 1, 2, 3. There's one circuit. Looks like a dinosaur. And here's another circuit. Alright. Which one's parallel? Which one's series? Why? Alright. If you said this is parallel because the resistors are parallel to each other, that is not right. Look, the current will go through one resistor, then the other, then the other. This is series. This one's parallel. Current will come out of the battery, and it'll be in the top node. it wants to go back to the bottom, so it'll go through this resistor to the bottom node and then back in the bottom. Or it'll go out the battery to the top node through the second resistor and then back to close the loop. Or from the top through the third resistor, then through the bottom, then the battery. There's 3 possible loops. 1, 2, 3. 3 loops for the loop rule. The current will never go through one resistor, then the other in series. They're parallel. 3 parallel choices to complete the loop. You might say, oh, current could go through like this. That wouldn't happen. If current goes through one resistor, it'll be already at the right voltage and wants to go back down to low voltage, back to the battery. It won't actually just go some other crazy path for no reason. So series, parallel. So hopefully you can think back to the tank of water I drew. If you have 3 pipes in parallel, that allows more flow. It's basically less resistance. If you have 3 pipes in series, that allows less flow. There's more resistance. That resistance we're going to call Req. So let's start with a simple series circuit. This is all series stuff. Okay. Let's say we have an 18-volt battery. And we have 2 resistors. Six ohms and 3 ohms. All right. We know V equals IR. I'll call this I total, IT for I total. And this 18V, we'll call that V total. There is no other V, but for now, this 18V, that's the total V. 18 volts. Okay. We know V equals IR, so if you want to find I total, it's V over R. But is it 18 volts over 6 ohms or 18 volts over 3 ohms? It's neither. If you want to find I total, well, it will be V over R. It will be V total over some R, but not the 6, not the 3. It'll be V total over some other R, some REQ. REQ is the equivalent resistance for the whole circuit, or the equivalent resistance for both resistors. What is the 6 and the 3 equivalent to? You might have a good guess, but we gotta make sure. So V equals IR, it's true for the whole circuit. I total equals V total over REQ. I would call it R total, but it's not just the total all the time. But this is also true for both circuits by themselves. So this 6 ohm resistor, let's say the voltage, well, the resistance is 6 ohms, yeah. Let's say the current through the 6 ohm resistor is I6. And the current through the 3 ohm resistor is I3. I3 might be the same as I6, and they might both be the same as I total. But for now, let's call them I6. And the voltage drop, let's say my hand is a voltmeter, I connect it here and here. The voltage drop is unknown. Let's call it V6. The voltage drop from here to here will be V3. Maybe V total equals V3, maybe V total equals V6. Maybe they're all equal, but for now, let's just write out their formulas. 3 ohms equals V3 over I3. So please ask me, the 6 ohms is the voltage across the 6 ohm resistor over the current through the 6 ohm resistor. The 3 ohms is the voltage over the 3 ohm resistor over the current through the 3 ohm resistor. All these things are true. Now we gotta make an important realization about I total, I3, and I6. And then we gotta make an important realization about V total, V3, and V6. Okay. First one is based on Kirchhoff's junction rule. For every junction, and that means every point in the circuit, the current in equals the current out. So look at this junction, this junction, this junction, every junction. If for every junction, I in equals I out, what's true about these currents? All right, baby, what do you see? Tell me about this junction right here. The current going in is I6, and the current going out is I3. So they must be equal. Yes, excellent job. I3 equals I6. Look at this junction and this junction. What do you see? The current going in to the battery is the current coming out of the 3 ohm resistor. And the current coming out of the battery is the current going in the 6 ohm resistor. They're all equal. Amazing job, Daisy. Thank you. I total equals I3 equals I6. Very good job. Now we gotta find a relationship between these three. Here's my loop. The whole loop will have a chain of voltage of 0 volts. So 0 volts equals 18 volts minus I6 R6 minus I3 R3. R6 is the resistance of the 6 ohm resistor. R3 is the resistance of the 3 ohm resistor, which I know. It's 6 ohms and 3 ohms. R6 is 6, R3 is 3. But I wrote them this way for a very nice reason. What can I substitute if instead of R6, R6 and I3, R3? What substitution can I make to make physics awesome, even more awesome than it already is? Because of Ohm's law, I6, R6 is V6. Amazing. If this is true, the total voltage is V3 plus V6. Be careful. They look the same, but they're not. I total is I3 equals I6, but V total is V3 plus V6, not the same thing. Once I do that, I can do some very quick math. I mean, medium speed math. Okay. If V total is V3 plus V6, that means 18 volts is V3 is I3 R3, so it's I3 3 ohms plus V6, which is I6 R6. I6 6 ohms. Oh my gosh, amazing. Since I3 and I6 are the same, I total is 2 amps. Does that work? If I total is 2 amps, V6 would be 12 volts, and V3 would be 6 volts. 12 plus 6 is 18. It all works out. Amazing. Physics worked. Great job. So if all you want is a shortcut, here's the shortcut. Well, V total is the sum of the V's. So it's V3 plus V6. Well, that's equal to this. So V total over I total is V3 plus V6 over I total, which is V3 over I total plus V6 over I total. Well, that's V3 over IT is V3 over I3, which is also V6, and V6 over I total is V6 over I6. REQ is the sum of the R's. Just soak it in and be amazed for a bit. These are the important rules for a series circuit. All the currents are the same. All the voltages are not the same. The voltage is the sum of the voltages of all the parts. And REQ is the sum of all the R's. Okay, now for parallel circuits. You can take a break if you want to come back to this tomorrow. It's going to look the same. It's not the same. Same voltage, 18 volts. Same resistors, a 3 and a 6. But now, as you can see, they're parallel, not in series. This is still true. This is still true. These are still true. What about this? Remember the junction rule. I in equals I out. So here's the junction. There's I in. Here's one I coming out. Here's another I coming out. How are IT, I3, and I6 related? The current coming in is IT. It splits. So the sum is equal to the total. This is not what we had last time. Before it was IT equals I3 equals I6. Now IT equals I3 plus I6. Okay. Now we're using loop rule to talk about VT, V3, and V6. But don't actually do it. Think conceptually. What loops are there? What must the voltage drop from here to here be compared to here to here, compared to here to here? Here's one loop. If the left side is one loop, the voltage gained equals the voltage lost. So the voltage 18 volts equals this voltage, V3. If the outside's a loop, then this voltage equals this voltage, Vt equals V6. And if you did the right side loop, which would be weird because one current will be negative, but it'll still work out. You'll get V3 equals V6. They're all equal to each other. It looks like what we had last time, but it's not the same. For parallel, the rules are reversed. The voltages are the same, the currents are split. In series, the currents are the same, the voltages are split. So we can solve. It's a little easier actually. I6 is 3 amps. No, sorry. Yes, I was right. I6 is 3 amps. I3 is 6 amps. Nine amps. Remember, we got 2 amps for series. We got 9 amps for parallel. Series circuits decrease the current. Parallel circuits increase the current because there's more paths to flow through. So we get a greater total current. And this is obvious. So that was easy. This is going to be a little trickier to find Req. For this circuit, it would just be, we know it should be 2 amps. So this is our answer, our final answer. But what's a shortcut? Due to reasons, it's hard to find Req. The shortcut, it's much easier to find 1 over Req. So we're going to do that. 1 over Req, well, if Req is this, 1 over Req is this. Okay, cool. Oh, same thing. I total is the sum of the i's. Well, every v is the same as v total, so this is the sum of I over v. And if v over I is r, I over v is 1 over r. I erased it and I wrote the same thing. If you have a bunch of resistors in parallel and you want the equivalent resistance for all of them, add up the sum of their reciprocals. That's not the answer. That's the reciprocal of the answer. So to find the answer, you do 1 over the sum of the reciprocals, or the reciprocal of the sum of the reciprocals. So let's try and make sure it works. 1 over r, so it's 1 over 3 plus 1 over 6. 1 over 3 plus 1 over 6 is 2 6 plus 1 6 is 3 6. So it's 1 half. 1 half is not the answer. 1 half is 1 over Req, so Req is 2. Sorry, not 2 amps, 2 ohms. But we did get the right answer. So these are the rules for parallel circuits. I is the sum, V is the same, not the sum, and 1 over Req is the sum of 1 over R. Looks very similar to our other rule, but it's not the same. So that's parallel as opposed to series. Those are the 2 shortcuts. Anything else to say today? We're going to look at something very, very fancy, very, very briefly. So we got the rules for parallel and series circuits. Looks like a great circuit to me. 12 volts, let's say 12 volts. For some reason, voltages are almost always like 6, 18, 12, 24 in problems like this. Here's the circuit. Here's another circuit. Okay. So these are called complex circuits. They're not parallel or series. They're both. I'll keep it short and sweet. If you see these circuits, you can't say, oh, they're all parallel, because they're not parallel. If this were all parallel, the current would go through this circuit, the current would go through, sorry. If this were parallel, the current would go through the 6, or the 3, or the 2. That's not what happens. The current goes through the 6 and the 2, or the 3 and the 2. Not 6 or 3 or 2. Same thing. This is not series. The current doesn't go through the 9 and the 6 and the 3. It goes through the 9 or it goes through the 6 and the 3. So, these circuits are neither parallel nor series. They could be called combination circuits if you want to give them a name, which you might. Okay. What do? You can break the circuits down piece by piece. Yeah, this circuit is in series, but these two are in series. Yeah, these three resistors aren't in parallel, but these two by themselves, they are in parallel. So this is a series. RQ for a series is the sum. And then this is in parallel with this series. So 1 over 9 plus 1 over 9 is 2 over 9. REQ is 9 over 2, 4.5. That's for, the 9 is for just these two. The 4.5 is for all three. 4.5 is REQ. V equals IR. So I will be 8 amps. These are parallel. So REQ will be 1 over 6 plus 1 over 3. That's 1 over 2. Then reciprocal again, because you have to find the reciprocal for parallel circuits. So it's REQ equals 2 ohms. And then this is a series. This is not in series. The 2 ohm is not in series with the 3 or the 6. It's in series with the combination of the 3 and the 6. So REQ for the whole thing is 4. And thus I equals V over R, 3 amps. If you want me to talk about this more in class, I can. You probably won't care unless it comes up in your project, which it might. So be ready for that. See you later. Bye. Just kidding. See you later. Bye.